Hello, I hope everyone is doing well. Right now, I'm going to try to go over an intro for the macro description of radiation. In this, we'll be going over the units, so I'm using astronomy units. I will be going over solid angle briefly, the energy density, U, the intensity or the brightness I, which is energy flux for this, and then the mean intensity JV or J nu, and then its relation to energy density and energy flux in this case. So first things first, the units. So here we are using CGS units. Comparing that to SI units, the normal units that you'll see for energy, for example, it is the erg. The first time I ever saw this, I was confused as I thought, why is someone like putting their grievances on this page? But anyhow, for force, it is the dyne right here. Another fun word. And of course, its relation is the Newton. And for energy, the erg is related to the joule. Mass, we're looking at the it will be in terms of grams. Normally, people use kilograms for SI units, not here though. And then for length, it will be in centimeters versus 10 to the power minus 2 meters. This is just because it makes things slightly easier for astronomy. Personally, I'm not really an astronomer, but since I've taken this with astronomers, I normally use it in the astronomy units. Also, I really love the term. I really love the erg. I think it's a fun unit. But anyhow, going over solid angles briefly is something I might actually do, explore further on like a further topic, or explore more on another topic. But basically, single point right here. This is the radius r, and this is right here is the area. Essentially, it is just to put this in basic units. The solid angle is the area over r squared being like the distance for this. If you put that in differential terms, the solid angle is a over r squared. And in easier differential terms, sine theta, d phi, or it's equal to, the solid angle is equal to this. It's measured in steradians, which is interesting. They're also called SDR, because if you look at the units for a squared, that is centimeters squared over centimeter squared, which is actually equal to, it's unitless. The same thing with radians too. Anyhow, the solid angle helps us understand this a lot better from a point. So we will be using this. U is the energy density. The energy density is taking ergs per, energy density per centimeter cubed. So I'll be looking at like T, this is energy density. But we will also be looking at in terms of frequency as well, as that is also quite a helpful topic. And so then that would be in terms of energy density in hertz right here. So now, and this would be where U is equal to UV or d nu differentiated by nu. So essentially it would just be differentiating out this hertz term, this frequency term. Anyhow, let's say that there is a bundle of rays, or a set of rays that are completely straight. And then we put this over, that's not what I want. Right here. straight here. And we take some cylinder over this, and then the solid angle as well, of course. So we terms of d nu, dA. And this right here is going to be in terms of dl, which is equal to c dt. And that is just because v is equal to, or the velocity is equal to x over t. This we're looking at the speed of light because we're looking at photons, and then length is equal to ct, which is why we have that. Also, things to note, since this is macro, we need that length to be much larger than the wavelength, or else that is going to be cause a lot of problems. It won't work, pretty much. So we want this in terms of the energy. Now, one ray is going to be infinitely small, but we're going to assume that this is a bundle of rays, so its energy is at least not neglectable. Or if we want to take it for a single one, it would be infinitely small. And then we see dA, dt, because dA, right here, the area from here, and then dt, and then c as well, because of the length, of course, that we're looking at. And then we have it by the solid angle, because we're looking at solid angle right here. And of course the frequency, because we want in terms of frequency as well. So putting this together, what does this mean? Well, this means that the energy density in terms of the solid angle is 1 over c, because we took that c out because it's constant. And it's the energy, well, so it's shaping up to what we want, per the area, and then dt, d solid angle, and then d nu, which is going to be equal to that erg centimeter squared hertz, as we have seen before. Why is that? Well, erg because of the energy, and then within the speed of light, we have centimeters and seconds. That seconds are going to be canceled out with this seconds right here. The centimeter over here is going to be multiplied by the area, so we get cubed. And then solid angle is unitless, and then of course we have the hertz right here. So now let's look at some intensity. This is the brightness, is going to be in terms of energy per second, centimeter squared. This is the energy flux. Now let's take it. Now we want to know this ray, in this case. I want to take this solid angle, dA, the solid angle right here, and we want to find the energy going through here, because as we talked about in the first video, radiation is, a lot of it is just a change of energy from rays, so energy is going to be the key term we need, through the area within a time t, and we want that frequency in there, nu. So what does that mean? We put that all together when we're looking for the energy. Well, we're going to get the intensity, of course. Then we have dA, because we're assuming it's going through this area right here. Then we're looking at dt, because we want to know it at some function t, so we want to multiply it by t or some differential of t. We also want to know it by the frequency, as we said right here, and by the solid angle, as we are taking the solid angle over here. So what does that mean? Well, when we put this all to one side, we have, you guessed it, over dA dt, d nu, d solid angle. And then this is going to be equal to the erg, the energy per squared, and hertz. And of course right here we have the energy flux, as we talked before, per sub time of nu, as we're also taking it by the frequency as well. So perfect. So let's wrap this up by talking about JV briefly. which is the mean intensity. The mean intensity is the direction averaged specific intensity. What does that mean? Well, it is JV is equal to 1 over 4 pi, because we're taking it over, assuming it is like a sphere, IV d nu. Oh, excuse me, that's not correct. It's not correct. The solid angle. And we also know that nu is going to be equal to 4 pi over c JV. Why is that? Well, that is because I need to talk about the relation between urgency and IV. So we know that this is going to be equal to the energy density in hertz. We know that IU is equal to ergs, centimeter second squared, in hertz. So what is this going to be? We'll call this A. What do we need to multiply this in order to get this other side? Well, A is going to have to be equal to, we're going to have to remove this S right here. So this S, we're going to need to multiply it by another centimeter squared. And what does that look like? Well, if we have centimeters over seconds minus 1, that's equal to the velocity. So in this case, and we know that the velocity we're going to be using is going to be c. So what does that mean? That means that v nu naught is equal to 1 over c IV. This relation. And that makes it much easier to see why this is equal to this right here. Why? Because we need to multiply out this, or divide out this 4 pi. We need to take in this c, and j is really just equal to the specific intensity with the solid angle integrated out. So thank you for watching. Let me know if I've made any mistakes, and thank you again.